Marta is going to talk about black holes and AGN and hierarchy. First for an hour and a half, then a coffee break, and then another hour and a half. So go ahead, Marta.
Thank you, Yaki. Good. So yesterday, I hope that Roberto's talk made you curious about hierarchical black holes and AGN. So I will focus mainly on the theoretical modeling, but I will introduce it through observations, and also, if we have time at the end, connect back to what we have seen. So as a bit of introduction, this is not a comprehensive lecture. I mean, in 3 hours, you cannot compress everything there is there to know. And it's also my personal view, informed by reading hundreds of papers over the years. If you want some reviews, there are, I mean, this is a field that there is really pre and post JWST. There is a significant difference. I'm not really sure yet how to connect the two things or what we should believe. But you can find a summary of what we thought before JWST in these reviews. And then conveniently, just for you, I put on the archive this week the write-up of the lectures that I gave at another school. So there you have really pretty much all the material present here. OK, so let's start with just massive black hole basics. I assume that not all of you work on AGN and massive black holes, so just some background. Massive black holes in galaxies. So massive black holes, of course, are those that power AGN. But something that I think is important to keep always in mind, especially when we talk about the theoretical modeling of black holes, is the scales. So if we start with something like a Milky Way, a dark matter halo with a mass of about 10 to the 12 solar masses and a virial radius about 100 kiloparsecs, then the visible part of the galaxy is about 10 times smaller and in both mass and size. And then when we add the black hole there, well, in principle, we should not be able to see this dot. A black hole is characterized typically by 3 physical scales. One is the Bondi radius, which is the radius at which gas becomes bound to the black hole. It scales with the black hole mass divided by the sound speed squared, and is about parsec scales. The sphere of influence is the same, but for stars. So here, sigma is the velocity dispersion of the stars, and it's again in parsec scales. And then you go to the event horizon, Schwarzschild radius, last innermost stable circular orbit. They're all of about the same size. And here, the denominator, you have the speed of light. So you see that the difference between the sound speed, tens of kilometers per second, velocity dispersion, hundreds, and the speed of light, 100,000 kilometers per second, gives you microparsec scales. So if we just want to model, theoretically, one black hole in a Milky Way, our own black hole is called Sagittarius A star, has a mass of 4 million solar masses. You already have from microparsec to about 100 kiloparsecs. So if you want to put this in a cosmological setting, you understand that the scale problem is a key bottleneck, not only in terms of physical scales, but also in terms of time scales. Matter moves at the speed of light near the Schwarzschild radius to have very short time scales. The age of the universe is 13.7 billion years. If you want to run a simulation with a time step of 1 second for 13.7 billion years, well, it will take billions of years as well. So we have to make simplifications. More about what we know of black holes in galaxies. This is the local view. I think Roberto showed this, or some version of this. Over the years, starting from the late 90s, early 2000s, correlations have been found between a black hole mass and other galaxy properties. The first one was bulge luminosity and then mass, then velocity dispersion, and then we attempted to find a relationship also with the with the stellar mass of the total stellar mass of the host galaxy. Now, this is discussed very clearly in many papers. Here there are some examples. So what is found typically is that the relationship between black hole mass and bulge mass is very tight for galaxies that have a nicely defined bulge. For galaxies, for small galaxies, dwarf galaxies, or galaxies with pseudobulges, then the relationship becomes murky. The relationship between black hole mass and velocity dispersion is very tight and seems to be valid pretty much at all scales. Here there is there has been a lot of discussion about what is sigma. Sigma here is typically defined, I mean, the people have converged with the definition that is the line of sight integrated velocity dispersion at the effective radius of a galaxy. So it's a very specific definition. And finally, we have black hole mass versus stellar mass. We have known that this is a looser correlation, meaning that the intrinsic dispersion is larger. So if you were to think like John Carmody, who wanted to use this relationship to measure black hole masses, you cannot use the stellar mass. Because if you have an uncertainty of 0.8 dex, well, basically you don't know your galaxy, your black hole mass within 1 order of magnitude. But when we proposed to use the stellar mass was really to look at galaxies where measuring the bulge mass or the velocity dispersion defined in this way was not possible. And we were thinking specifically of high redshift. Yes?
The black hole mass is measured by a disk.
The black hole mass here is measured with different techniques. Here, here there is no difference. So for quiescent black holes, that are for the most part these red ones, because they're in elliptical galaxies, you use stellar dynamical measurements. What means is that you're trying to find the signature of a deep potential well as straight by the orbit of stars. So in an ideal world, I don't think I have a slide here. In an ideal world, you should see a Keplerian rise in the velocity, in the velocity of stars. In reality, it's not this simple. You have to use something called Schwarzschild modeling. So you model all the orbits of stars in a galaxy and trying to find the best match in a statistical way with the velocity dispersion. Actually, you should use all the moments of the velocities to see what is really the potential well determining the orbit of stars. These can also be performed with gas dynamical measurements. So you try to do the same, but with the motion of gas instead of stars. It's a bit more complex because gas is collisional, so you can have shocks, you can have different motions. And so it's simpler in some sense, and it's more difficult in others. And finally, for AGN, what is typically used are scaling relationships. So there is, for AGN that have been monitored for a very long baseline, you can use variability to infer the size of the region that is in Keplerian motion around the black hole. Gas is not always Keplerian, but you make this assumption that it's assumed to be virialized. So by using these long baselines, you try to measure through the difference between the arrival time of photons, the size of this region. And then what it was found is that the size of this region correlates with the luminosity of the continuum, I think at 5,100 angstroms. Anyway, there is a correlation. So at this point, you measure the luminosity of the AGN. You infer the size of the region that is in Keplerian motion. You measure an emission line, which gives you the Doppler shift, so the velocity of the gas. Once you have the velocity of the gas and the radius within which this gas is moving, you use the virial theorem to infer the black hole mass. And this particular point, I was not going to touch on it, but it's one of the key points that we have now at high redshift. So these were all derived. So this final step where you use correlations of correlations to infer the black hole mass is what is now being discussed as, is it still valid or not? Because, for instance, the ratio between the strength of the lines and the continuum is very different in these high redshift galaxies compared to local galaxies, which means that there are different excitation mechanisms at play. And there is always this assumption of Keplerian motion everything we realize, that is always a bit uncomfortable. Alessandro Marconi has shown in papers that if you have radiation pressure, obviously gas is not moving in circular orbits, is being also perturbed radially. So while in these cases, masses are usually relatively well known is within a factor of 2 to 5. So the famous black hole M87, it's huge in the sky. You know that its mass has been measured with gas dynamical measurements, with stellar dynamical measurements, and then with the Event Horizon Telescope. And, well, let's say that they didn't agree until they decided to agree. I mean, it's I would say that, I would keep these masses as, within a factor of 2 to 5, I think that they're reasonable. For high redshift, I think the uncertainties are a bit larger. Okay. So when we go to high redshift, I think that, Roberto already mentioned this. If these red points are the local counterparts, the high redshift shown here in blue and yellow show a very different picture. Black holes are overmassive. Yes. Now, something that this plot puts together a few different things. For the JWST observed systems in yellow, you have actually stellar masses. And, yesterday you have all played with Seagal, so you know exactly how stellar masses are measured. Then something else for the high redshift quasars. In particular, here you see Izumi, so the gray points that I'm sure you're not seeing but are up here. These were actually dynamical masses measured with ALMA. So part of the confusion at high redshift, and I mean, especially at the beginning, was to use different tracers for the mass of the host. This now has been improved just because, for instance, you use only JWST data where you measure either the stellar mass or the dynamical mass. So an important point that this has been, again, seriously, it's 15 years that I say this, so please listen to me once. When we compare correlations, you cannot just pick and choose whatever you want. If you use correlation between black hole mass and bulge mass, you have to measure the bulge mass. If you use a correlation between black hole mass and velocity dispersion, you have to measure the stellar velocity dispersion. If you use the dynamical mass, you have to measure the black. And it's really important because, in particular, because the one case in which most people just mix and match as they wish is the difference between bulge mass and stellar mass. Since the relationship at threshold 0 is well calibrated for bulge masses, and it's a tight relationship, if you use it for galaxies in which you don't know that there are bulges, you're certainly making a mistake. That's very simple. But besides this, besides the definitions, that I think, and now at least some people agree, an important point, and already Roberto mentioned this, is that there is a difference between saying the black holes that we detect are overmassive and high redshift black holes are overmassive. The first is a statement on your sources. The latter is a statement on the population. If you want to make a statement on the population, you have to infer what the systems that you cannot detect are. So since, I think, early 2000, actually, this is called Lauer's bias, but it was first introduced, oh gosh, I don't have the reference here. But in the PDF, you have the correct references. It was very soon realized that when you select quasars or AGN by flux limited survey, every time you select by luminosity, basically, black holes that are overmassive with respect to the mean relation would be brighter and therefore overrepresented in the selected sample. This is simply an effect of the galaxy mass function. If you have a correlation between black hole mass and galaxy mass, it means that you have many more small galaxies and high mass galaxies. And then if you assume that the luminosity of the black hole scales with the Eddington ratio and the black hole mass, then you can very easily show that an overmassive black hole in a small galaxy at fixed luminosity is much more likely than an undermassive black hole in a massive galaxy. This is just because this is a steep relationship. So basically the result is that if you start with a mean relationship that is shown here in yellow, I don't know if you can see it, but I'm using the laser pointer here. And so you have a global population as shown in here in black. If you apply a luminosity cut, you will see only the red black holes, and they will have a relationship that is shown by this blue line, which is shallower and with a higher normalization. So again, this is really, really, old work. Then you can do this exactly with the JWST specs for different selections. Obviously, if you do this on your sample, you have to use your own selection criteria. But you can show how, if you start from this intrinsic population, once you start applying cuts for the ability to see the broad lines, the ability to just have the system in your JWST selection, you end up, after applying everything, with this observed distribution. So this is the intrinsic, this is the observed. Again, same thing, higher normalization, shallower distribution. And for instance, this was work by Junyao Li. You can show that the JWST detected AGN are still consistent statistically with a non-evolving black hole mass stellar mass relationship. Now, I'm not saying that there is no evolution. Don't get me wrong. I mean, if you ask me, I can also tell you why I think there should be evolution. My point is that whenever you make a statement or any statement, you have to back it up by the statistical background. Then, last point. It's not that I'm speaking, no, last but one point about the background. So if we put this plot, and you have seen different realizations of this figure, when you have black hole mass as a function of redshift, quasars, and JWST AGN. I made this plot, I don't know, I think a year ago or so. So it's not complete. And just also keep in mind everything we said with Roberto, masses of galaxies, Balmer break, which is not a stellar Balmer break, emission lines that you use to measure black hole masses that may be not with exponential wings. So take all these masses with a grain of salt, please. But then you can do a simple exercise of growing a black hole with an initial mass m0 to a given time t by integrating this equation. This is just the equation of the growth of black holes at a given Eddington ratio. Here you have basically two parameters. One is the Eddington ratio of a black hole at a given time, and the other one is the relative efficiency of the black hole. So here I fix the relative efficiency to a value that I think is 0.1, and I let the Eddington ratio vary. Either a fixed value of 1, so black holes are always radiating at the Eddington luminosity and accreting at the Eddington rate, 30% of this, and then a random combination of sub-Eddington accretion down to 10 to the minus 4 and super-Eddington up to 10. Here I took two initial black hole masses, 10 and 10 to the 5, and I let it go. And you can see that, honestly, I mean, people are, I don't think it's so dramatic that you cannot explain these black holes. I mean, the constraints from the higher redshift AGN are kind of the same as the higher redshift quasars. That doesn't change much except in numbers. But you can see here that with either heavy seeds and 30% Eddington, or small seeds and 100% Eddington, or even better, with random combination of super and sub-Eddington accretion, you can explain it. Now, this is an analytical model. This is not the real universe, but just to give you an idea on the scales. That black holes have to grow efficiently. They have to start kind of massive-ish, but not in a way that was different of everything that we knew from the higher redshift quasars. So the problem has kind of the same. What has really been more problematic, though, is the number density. And again, this was covered by Roberto. So before JWST, the expectation for the number density of AGN was one of these blue curves. This was the extrapolation of the luminosity function of quasars that works, as far as I know, reasonably well at low redshift, down to redshift 3 also. But if you look at high redshift, the moment JWST started taking data, the number densities that were observed were significantly higher, 1 order of magnitude, or at redshift 7 to 8, I mean, completely off scale. So it's really the number densities of these black holes, I think, that are more important, or the connection between what we knew and what we didn't know. Now, interesting point that I keep on making is that if you asked me or anyone working in this field in theory in 2022 to give you the predicted number density of AGN, this is what we had. So this is a compilation of cosmological simulations in 2022, so before any JWST detection of AGN. And this is a compilation of theoretical models until 2022, so before data. If you look at the number densities here, and you compare them with what we find with JWST, they're actually in very good agreement. So what is the problem? The problem is that if you compare them with the previous observations, they are not in agreement. So what happened is that for 20 years, we theorists have heard people telling us, these black holes are not there, your models are wrong. And now they're telling us, oh, we found these black holes there, you never told us that they were there. So, stealing this from Yoki, our work in the last 10 years has been mainly to try and reduce black hole growth because they were telling us these black holes don't exist. And now we're trying to grow these black holes as much as possible. So I will touch on the physics that goes into accretion, but really be careful about decoding the titles of papers and about surprising results. It's true that there are things that we have to understand, lots of things. I think that in the last 2 years, my main sentence has been, I am confused. I'm not saying that we know everything. I'm just saying that, be careful about comparing with theory. Just be aware that there was theoretical work there. And Roberto has already talked about the weirdness of JWST AGN, lack of X-rays, possible widespread supereddington accretion, and I will say a few words about little red dots. The mystery of little red dots, it's a fascinating history. This slide was inspired by Vasily Kokore's talk at a conference in which he very nicely went through the history of the discovery of little red dots and the weird things. From the existence of broad lines, this V-shaped AGN, they have their dust poor, they don't have X-rays. Like most of the AGN, the sentence about lack of X-rays is not only for little red dots. Not much radio, very high number densities, and possibly high stellar densities. Now, in March, I was in Geneva, and I was talking to Pascal Oesch, and he showed me a spectrum and said, do you know what this thing could be? So it was a very steep Balmer absorption on an object, and the whole point was that Ran Naidu wanted to call it black hole star. And I was, no, you cannot use black hole star, because it reminds us of quasi-stars that I will define in a minute. So we cannot make these things. And then, we discussed about what they could be. I was super Eddington, edge of the accretion disk, blah, blah, blah. And then we keep on talking. We go to dinner, and at some point but this black hole star actually has the same properties of a quasi-star. So it was actually quite cool. So Mitch Biegelman has worked now for many years on these objects that are called that he called quasi-stars. They are small-ish black holes at the center of a gaseous envelope. So it's basically a star which is supported by black hole accretion rather than nuclear fusion. And if you look at the characteristics, well, except that the intrinsic spectral energy distributions should be a black body, low temperature, 4 to 10 K. But there is a very nice paper by Bigelman and Dexter in 2025. These objects kind of look like these weird little dots with all their properties. So I mean, I'm just very intrigued that these objects that I think when Mitch proposed them, I was part of the paper. Martin Rees and I were, really? And now well done. So this is something, just to complete the kind of picture that we have at this point. And now what I want, before, so I will stop in a few minutes if you have questions, because then I will go to the actual lectures, kind of more structured and boring. Well, boring the same, but yeah. Any questions? Yes? Is this what you mean? Is this the plot that you were referring to? Well, it's more that they are more than expected from the extrapolation of this. So if you assume that the physics is the same at redshift 3 and redshift 6, meaning that you have accretion on black holes, at redshift 3, if you extrapolate the quasar population, you get to the AGN population in a smooth way. Here, if you extrapolate from the quasar population to the AGN population, you don't have the same smooth evolution. So it's, in fact, there are a few papers showing that to explain these are for the most part littler dots in terms of selection. You can show that you can explain this kind of difference by assuming that there is a dual population. The low mass black holes, little dots, are kind of super Eddington-ish and have a narrow Eddington ratio distribution, while the quasars are the standard AGN are a different population. I'm totally open to anything. Other questions? Yes?
So I was wondering about the little dots. So what exactly is missing for people to agree on, like, what type of objects they are? Because you often see people publishing different kind of theories and findings, some number of objects that match their criteria. So I'm wondering what is missing for people to converge on.
Well, first of all, in terms of observations, a uniform selection. Different groups select little dots in different ways, and so they get completely different number density, completely different properties. So already working within a unified framework, I think it helps, because then you are, okay, objects that with these characteristics have these number densities. But I think that the main point is that all these things together were not seen before in any source. So it has to be something new. And what is the correct hypothesis? I think now there is a bit of a convergence with this black hole star, quasi-star, just to explain the Balmer breaks. Then you have the lack of dust, and you are okay, but so if I have 10 to the 8 solar masses of stars, how can I make no dust? So it's really, I think that what is cool is trying to make all these pieces fit together. I mean, it's the first time, honestly, it's never been so much fun. I mean, I'm very confused, but it's the first time that I actually have something to play with, a mystery to solve. Then I don't have time to do much research, but still, it's super exciting. But I think that this is the point. It's like with gamma ray bursts when they were discovered, people didn't know what they were. And so this is, and I think it will take, a few years before we settle on something. Any other question?
Excuse me?
Yes?
I may misunderstand. Do you mean this later red dots have a possibility to be crazy star?
They may be. I mean, it is, if you look at this paper by Biegelman and Dexter, 2025, they really make the connection. So I think that the main problem there is that the intrinsic spectral energy distribution of a quasistar is a black body. So you should see a drop outside the temperature peak. And this is not a good fit for the data. But you could explain the Balmer absorption. You could explain the lack of dust, because basically you form only one star in the galaxy. You also explain the lack of host. There are similar models that have been proposed. Koei Nayoshi has a similar model, but this was the historical first. Mitch proposed this in 2006, so that's why I'm stressing his work.
May I ask more? So I think the quasar is the progenitor of your class black hole, right?
Sorry, the quasar?
Is quasars are the progenitors of your class black hole?
Yes and no. So the original model from Mitch was about black hole formation. Now I think that the question is more, what conditions do you need to have this type of picture? For instance, there has been a little red dot, the egg discovered at very low redshift. So in principle, if you look at Mitch's paper, to form one of these systems, what you need is very high turbulence to suppress star formation. He doesn't believe in Lyman-Werner background suppressing star formation. And so in his picture, you could have these happen at any time in the universe if you have sufficient high turbulence magnetic fields. So he proposed it initially as a way to form black holes, but in principle can be adapted to also later times in the universe.
I was wondering if the condition of forming quasars, it must be, it should be exposed to high, intense Lyman-Werner radiation.
Yeah, no, this is not Mitch's favorite hypothesis. He prefers high turbulence suppressing star formation. So you don't need a high Lyman-Werner radiation. It's work that he's done with Isaac Schlossman. So this would kind of decouple the formation of quasi-stars from being in the high-redshift universe at zero metallicity or extremely low metallicity. And you can have this at later times. Now, here I talk about Mitch's work, so take it with a grain of salt. And my suggestion is really to read his papers. Anything else? OK. So massive black hole formation. So now we are going to what we have just been discussing in some sense. What are the initial conditions? Everything goes back to the mid-70s, when Martin Rees outlines a possible model of formation of massive black holes in a galactic nucleus. So basically start from a gas cloud, and then you can form a massive black hole in different ways. Now, something I found very interesting yesterday when Roberto was talking about the standard way of forming a massive black hole, that's not standard for me. I never thought of a stellar mass black hole growing all the time to form a supermassive black hole. Probably, I would say that what Roberto described is the most natural way. If you don't want to have anything a bit exotic, a normal way of forming a black hole is just from the endpoint of a massive star, and we know that black holes accrete in the universe. But already from Martin's paper, what you see is that to form a really massive black hole in a short time, it's easier, I would say, to go through other paths that require other formation of supermassive star. This is for post-Newtonian instabilities, or dynamical effects in dense stellar systems. Now, what have we done since 1978? Not that much, really. I mean, no, we have done some work. But the main goal has been to, instead of starting from a gas cloud, they start from a cosmological environment and trying to predict the typical number densities of black hole seeds formed in different ways. So this was, in 2021, a collection of what we thought about black holes in the universe. You have stellar mass black holes, endpoint of massive stars, you have billions in the Milky Way alone. Massive black holes with uncertainties at the low mass end, but kind of well characterized from the mass of Sagittarius A star onwards. And then here, populating this region were the formation mechanism that we had thought about, including kind of exotic ones. Exotic for me as an astrophysicist. If you were a theoretical physicist or a cosmologist, these would be the normal ones and these would be the exotic ones. But you see that they populate a region in between the observations. Now, this was 2021. Nowadays, we think that the models based on stars and gas are more of a continuum, a distribution of different mechanisms, but not kind of separate boxes, which in some sense makes it a bit harder for observers to pinpoint what is the dominant mechanism or the most important, because you don't have separate boxes, but a bit of everything. So I will try to say a few words on each of these classic mechanisms, working on Martin's proposal. Remnants of the first stars. Andrea has explained you how to make the first star, so assume everything he has done and get to the end point of the life of massive stars, zero metallicity massive stars. This is important for black holes. So first, what Andrea already said is that the typical masses could be larger than today. But more importantly for black holes, when you have zero or very low metallicity, then the mass of the remnants, so when you have the end point of the life of stars, is very similar to the mass of the star itself. If you have high metallicity or lots of heavy elements, your opacity is much higher. So when you have pulsations and winds, lots of stellar mass is ejected. Low metallicity, low opacity, so the mass of the remnant is a large fraction of the initial mass, about 50% or so. So if you start with the black hole of 10 to the 4 solar masses, with a star of 10 to the 4 solar masses, you end up with a black hole of about 5,000 solar masses. If it's a solar metallicity, you do the same. You start with 10 to the 4 solar masses, you end up with 10 solar masses. So it's not particularly helpful. Also, this was proposed in early 2000, Marta Volonteri 2001. And at the time, the picture of the first stars was that in each mini halo, you form one star. This star is at the center of the halo and is as massive as possible. This was, if you want to have the perfect setup to grow a black hole, that's it. As time elapsed, people started thinking that you have multiplicity. So in a given mini halo, you form more than one star. If you have more than one star, you share the gas mass. So the masses are not as high as they used to be. So this is why this has lost a bit of favor, just because the typical stellar masses are not as high and the positions of the black hole were not so favorable. Then the other model, this appeared also in 2003, Volker, Brom and Loeb, and then more papers. These are based on supermassive stars or quasi-stars, and it's often referred to as direct collapse. Now, this is not technically direct collapse, so in the field we try to avoid using the word now, because direct collapse may lead people to think that gas collapses directly into a black hole, which is not the case. You go through an intermediate phase of supermassive or quasar. Now, the goal of these models, in some sense, was to form more massive black holes. And you can, again, in the early days, early 2000s, we thought that we could get to something like 1 million solar masses. The conditions that were suggested is that star formation is suppressed in a mini halo, and all the way until the halo the mini halo becomes an atomic cooling halo, so with a mass of about 10 to 8 solar masses. And at this point, you start cooling, but all the gas cools kind of coherently, accreting on a single point in the halo, so a single protostar. And the condition to have the star not evolving on the main sequence in a normal way is to have an incredibly high accretion rate on the star, 0.01 to 0.1 solar masses per year. So basically, you have the gas in the halo that slowly accretes on a single point, and this point turns either into a quasi-star, into a supermassive star, or something like that. So in some sense, it's star formation at its extreme. Now, if we take this specific type of models, which are the most popular, although now they're kind of losing popularity because of some problems, you need primordial gas composition or extremely low metallicities down up to 10 to the minus 5. You need to suppress the formation of molecular hydrogen. Again, I refer to Andrea's lectures on how this happens throughout the whole life of this halo. Or you need to have strong dynamical instabilities, or a combination of the two. If we just focus on the Lyman-Werner background, meaning the dissociating radiation that keeps the molecular hydrogen from forming, it's kind of a vicious circle in the sense that you need UV radiation to stop star formation in this halo, but you need other halos to form stars if you want to have UV radiation. So it's kind of a combination of location of the halo in a nice spot where you are bombarded by UV radiation on all sides, but not having metals reaching the halo. So this figure shows the mass of a supermassive star that you can form as a function of the intensity of the Lyman-Werner radiation, which, okay, I don't have the units here, but I never remember J21 in which units it is. But what you can see here is that you need a value of the intensity that is of order of a few hundred if you want to have a star of 10 to the 4 to 10 to the 5. Now, the average intensity in these units is about a few. So you cannot just assume that the global UV radiation that you get from the superposition of all the stars in the universe will do this. You need some local radiation, local sources of radiation that will illuminate this halo and produce this very high intensity. But these sources should not be so close that when the stars explode and produce metals, they will reach this region. It's really a combination between, yes, I want to get UV radiation, but no, I don't want the metals. It's really a fine line to walk. And so, in fact, most of the problems with this model is really in the small number densities that are currently predicted, about 10 to the minus 6 to 10 to the minus 9 per cubic megaparsec, so much smaller than the number density of black holes we see. One can get intermediate mass supermassive stars, so 10 to the 3, 10 to the 4 solar masses, with a more moderate amount of dissociating radiation. You don't need this extreme hundreds of thousand times the average radiation. With 10-ish, which is something that you get very often, but a very active halo merger rate, you could still suppress the formation of molecular hydrogen, meaning the formation of stars in a halo. Here you can get stellar masses of about a few thousands of solar masses. I think that the key difference between the previous idea of supermassive stars and these very massive stars is really the environment where the stars form. For the high radiation, dissociating radiation case, what you expect is really the whole halo collapses, cools, and accretes on a single star. So it's kind of a spherical-ish environment with one star. In this type of picture, instead, you have something that is much more structured. So you have several regions of star formation. You see here, this is, for instance, this is literally the distribution of the masses of stars in this halo. So it's not something that is as extreme as before. You can have massive stars, but nothing. So, and you don't get to about 1 million solar masses. So this should be common, at least based on the calculations, this should be common. So you lose a little bit in black hole mass, but you gain in number density. Now, these are the two most popular mechanisms today. But I just want to highlight a few of those that were proposed over the years. So as I was mentioning earlier, the papers by Schlossman and Bigelman, where they suggested that global instabilities really transport angular momentum to the center. So you don't have to worry so much about intensity of radiation, but really global instability, meaning torques, super duper bars transport the angular momentum to the center. Local instabilities, so this is really Tumre parameter. So here, really you can think of this as a bar, meaning that you have this local instability transport mass in and angular momentum out. So you form a kind of low angular momentum region, a spherical-ish region. Major mergers between Milky Way-sized galaxies. This is a very extreme proposal in which when you merge Milky Way-sized galaxies at redshift 20, if you have as many as those, you can collapse everything into a black hole under GR instabilities. And I know that Andrea has worked on this, or specifically on understanding if this is feasible. But even if it is feasible, this should be so rare that doesn't explain the population of black holes that we see. And then convergence of cold flows and turbulence. That also, I mean, everything that gives you strong inflows in the local region can help. But so over the years, 1 and 2 has lost favor because cosmological 3D simulations don't see these effects, but beware of simulations. So I'm not sure yet that this should be abandoned. 3 and 4 simply because they don't explain the number densities of black holes we see. They may happen, just not explain what the bulk of the population. Okay. So at the moment, the type of models that we have seen are cases in which you form one star. And this star turns into a black hole, and that's your seed. As I said, all of these models have some problems. So POP3 stars, yes, you form POP3 stars. I mean, we expect that, I mean, without POP3 stars, we don't form metals in the universe like ever. You may form these supermassive stars, probably not with the number densities we need, but something that happens no matter what in the universe, just because we see it, is star formation, normal star formations. So, and also recently, JWST, but there were hints also before, and also the nitrogen abundances suggest that clustered star formation is a thing. It happens in the universe. When you have clustered star formation, then you trigger dynamical effects. So now, at this point, you're not talking anymore about extreme cases, extremely halos that are bombarded by extreme radiation, or a halo that grows extremely fast and staves off star formation that way. This is just, run-of-the-mill normal star formation. Well, kind of. What you need is dense star formation, what we typically would call a nuclear star cluster. In the Milky Way, in the center of the Milky Way, we have a famous nuclear star cluster hosting our black hole. So this is beautiful physics. It goes back to the 70s. but it was proposed as a way to form massive black holes starting in the early 2000s. And I have here, the seminal papers and then a few of the recent ones. And basically, it's what happens when you have a dense stellar structure that typically we call nuclear star cluster. This is the picture that we have at the moment. Then we can discuss how this ties in with cosmology. So this is just what I just said. Now, what happens in a dense star cluster depends on the relationship between the time for the dynamical effects to take place compared to the time for the stellar evolution and explosion of the first supernova. Now, the first thing that happens at this point, so no supernova has exploded. I'm only made of stars. The gravity acts on the stars, so the most massive stars fall to the center. And so this is what is called mass segregation. You have a stratified cluster with the most massive stars in the center, and then as you move out, lighter stars. Now, at this point, you have segregated the massive stars in the center in a small region, so they will start having dynamical interactions. They just don't have that much space to go. But any dynamical interaction, you have an exchange of energy, of kinetic and potential energies. And this will further modify the distribution of stars in the cluster, meaning that stars that get kinetic energy may leave the cluster. And so this affects the global energetics of the cluster. I'm not going into all the details. But this is called a runaway process, because the more you pack stars in the center, the more the stars pack themselves by these interactions, until basically they get so close by that they have to start merging. They simply don't have space to remain separated. Now, now here then there is a key point. Now, the typical assumption is that when two stars collide, they merge, and they make a more massive star. This may happen or not, but since we want to form black holes, we will assume that when stars collide, they merge. In reality, what we have to worry about is that when stars collide, their radius, they expand, so their density decreases. So at some point, you may have that stars pass one another. But if we want to form black holes, we have to assume that actually stars collide and merge. Now, at this point, you start forming a star that is growing by merging with other stars. The key point here is if any star explodes a supernova, you stop this process. So the time that you have to grow a star is the time on the main sequence of the most massive star. And so the comparison between the time on the main sequence of the massive star and the time for this process to happen sets the maximum mass of the star that you can form with this process, which is about a factor of 1,000 times smaller than the mass of the cluster. This is all work done by Porteous in early 2000. There are many papers recently, but everything was already very nicely explained there. Now, to have this, you can see here the dependencies. You want a compact and massive cluster with a typical mass that is relatively high. This is not always the case. So sorry, I was forgetting this. And again, here you need very low metallicity, not because you want to form massive stars at this point, but just because of stellar evolution, pulsations, and opacity, that even if you form a massive star at solar metallicity, you will end up with a tiny black hole. So there is more recent work, but Gaburov in 2009 wrote a very influential paper on that. Now, in the majority of cases, you don't have these extremely compact clusters that lead to core collapse. This process is often called core collapse before the explosion of the first supernova. So in the large majority of clusters, not all clusters, what happens is actually that you don't have all this runaway growth of a single star. But mainly, since you're forming in the center these massive stars, they start forming, not only merging with each other, but just dynamically interacting. They form binaries and triples. When binaries and triples interact with the single stars, then they are an extra source of energy that delays or even halts collapse. So at this point, you still have the same process, but you go a step further. So instead of segregating the massive stars in the center what you have now are the black holes, because they are the most massive systems in this case. Again, we are beyond the explosion of the first supernovae. We are beyond the explosions of supernovae. We have formed black holes. The lighter stars are really are still staying outside, and the black holes are the most massive objects. So at this point, I'm going quick on this. What you have is mergers of black holes in the center of the cluster. This is a bit more dangerous than the merger of stars, because when black holes merge, they emit gravitational waves. And this process triggers the a recoil on the merged binary. It's called gravitational wave recoil, gravitational wave kick, which has a speed of, well, from 0 technically, but from about 50 kilometers per second to thousands of kilometers per second. The escape velocity from a cluster, let's say 100 kilometers per second, much lower than these 1,000 kilometers per second. But so if you manage to retain your black holes, I mean, this is work that has been now received much attention in the context of LIGO, Virgo, Kagra detections. You can keep on merging and merging these black holes, again, if you're lucky, and forming a black hole a massive black hole with a mass of hundreds to thousands of kilometers per second. Now, an important point here is that since we are already dealing with black holes, we don't care about metallicity. This process can happen at any time in the universe. However, the time scales are much longer than if you think of these runaway mergers of stars. Runaway mergers of stars has to happen within 10 million years, because otherwise we explode a supernova. This usually happens on hundreds of millions of years, and forms black holes that are not super duper massive, hundreds of solar masses or so. So as I said, all this work has been now really refined to explain the gravitational wave detections by LBK, but it dates back to the 70s and so on. Now, the main novelty in the context of massive black hole that happened in the last few years is to realize that actually there is gas. If you are in a higher redshift cluster compared to a globular cluster today, you are most likely to have some gas around. And this modifies the picture, in particular, can increase significantly the mass of the black hole, about an order of magnitude or so. There also, I mean, the black hole can also grow by capturing stars. So on this baseline process in which you have everything happening kind of monolithically, now most of the work in the last few years has been to see how this proceeds in a more evolutionary way, including the presence of stars and gas. So to go back to what I was explaining, this is why I said, we have this mechanism, first star remnants, star clusters, supermassive stars that I just explained. And until recently, they were considered separate. But in reality, if we look at these really physically, they represent a continuum. So what you can imagine that as a function of the UV radiation, you may form a more or less massive star. And this is a dependence also on metallicity, as we said. So you can imagine that with very high UV radiation and very low metallicity, you form a single star in a halo. As you increase the metallicity or you decrease the Lyman-Werner radiation, you start forming multiple stars, of which one may be dominant. But eventually, at high metallicity or very low UV radiation, you actually form a star cluster. But once you have a star cluster, you enter into this regime, in which you may have the formation of a massive star or a massive black hole through dynamical processes. So it's really that the way I see it, I mean, perhaps this is wrong, but the way I see it is really that depending on the environmental conditions, basically the impinging UV radiation, the intrinsic condition, the metallicity, the density of the system, you may form a black hole in very different ways. So in the last couple of minutes on this topic, I'm not done yet. But just a few words about primordial black holes and cosmic string loops. So this is ways to form black holes before galaxies. They were suggested back in the early 2000s as well. And then the paper, I think, by Karen Silk in 2018 was instrumental at making this interesting again for massive black hole formation. Now, primordial black holes are dark matter candidates. And I think that the cool thing here is that the galaxy grows around the black holes rather than vice versa. So this eases some of the growth issues that we will discuss later on, as the black hole is really providing the potential well, and it is capturing everything that falls on it. Obviously, we have some caveats. So we know that stars form in the universe. We observe them. We don't know if primordial black holes and cosmic string loops. Cosmic string loops are similar to black holes and to primordial black holes. They are sources of large-scale structure of overdensities. And then the question too is, are they consistent with constraints? So just very quickly, primordial black holes are expected to form just after the Big Bang with a mass that is the mass of the horizon at that time. The most interesting ones are for massive black hole formation is what happens at pair annihilation, because this corresponds to a mass of about 10 to the 5 solar masses, which is the sweet spot for black hole formation, for massive black hole sits. What we have to be careful about is that a significant space of the number density, and here shown as a function of the dark matter density, and black hole mass is ruled out by various constraints. Some related to the CMB, cosmic microwave background, some related to the structure of galaxies or the X-ray background. XRBs are X-ray boundaries. So a large number of primordial black holes is ruled out by the observations. But since the number density and the mass density of supermassive black holes or massive black holes is very small compared to the total dark matter density, you can still fit primordial black holes in this picture. This is just highlighted here. So you can still accept that primordial black holes are the source of massive black holes. In the case of cosmic string loops, as I said, the similar picture. So they represent. These are developed in string theories for the most part. And when cosmic strings interact, if the loop becomes sufficiently tight, they can collapse into black holes. Don't ask me questions on this. if you have any questions, please refer to Bramberger et al. 2015. But yeah, so in principle, you can have high mass black holes up to redshift 30 or so. So I will just leave you with a picture. So if we forget about these exotic mechanisms that we can talk about, but if we just focus on the simple cases, we can deal with either monolithical collapse in a single halo, forming a very massive star, distribution of stars in various halos that perhaps are also related to star clusters, or pop-tree stars, which are kind of distributed in low-mass halos. So I will stop here for a few questions, just highlighting these various processes with some of the questions that I have myself. But please, let's see if you have different questions. Yes?
I think I was just a little confused when we were talking early on about direct collapse black hole scenario. I didn't quite understand how the stars, you said there's like a balance between the Lyman alpha radiation and the metallicity. You want enough radiation to dissociate, but you don't want the metals from the stars. But I didn't have a very clear physical picture of like, the diagram of like where the stars would be forming.
I'm sorry. I removed those lights because I thought that I didn't have time. But the picture is a bit like this. So perhaps we need light. So there are mainly two pictures. One is called synchronized halos. So I have two halos that evolve kind of the same time. I haven't really fully ever understood this, so please be careful. In which they don't form stars until, so this part for me is a bit, is where I don't understand, which is why don't they form stars? But anyway, so you have sufficient UV radiation coming from all the other halos to stop them from forming stars. And then let's call this halo B, and then call this halo A. Now, halo A starts to form stars. So they produce UV radiation that goes towards the other halo. and this is good because you want a lot of UV radiation impinging on your halo. After about 10 million years or so, these stars explode as supernovae. And at this point, you also have bubbles of metals. So these bubbles will expand. At the same time, the UV radiation is also continuing. So as long as the process happening in halo B of collapse and formation of the supermassive star is faster than the expansion of the bubble, then you can have the formation of supermassive star. Otherwise, you have too many metals, and so this halo would start forming normal stars.
That's clear. Thank you.
This is the synchronized halo, but the other point that is often made is if you have an overdensity, so many halos and protogalaxies, then you have a satellite halo that is falling in, a pristine satellite halo that is falling into this overdensity in a very similar way. And the second one has been studied in detail by Chon, Soon-Myeon Chon with cosmological simulations. Yes?
If primordial black holes exist, I mean, they would be kind of embedded in the CMB, I guess. Are there any predictions for like how we could be able to observe them?
Well, Massimo Ricotti, with Oestreicher and Mack, has written beautiful papers on this. So in fact, the limits that we have on primordial black holes are mainly on the CMB not being a Christmas tree. Okay. Yes.
So that's on their masses? Or?
Masses and number densities. Usually the assumptions is monochromatic mass distributions. If you assume that primordial black holes have an initial mass function of some kind, then all the constraints become weaker. then Bernard Carr has written nice reviews on that. Yes?
I'm wondering, are there any constraints on primordial black holes from simulation? Because I think if we have black holes from the beginning, then it changes all the picture of star formation. We have
Yeah, so there have been two types of simulation to my knowledge. I mean, I'm not a PBH type of person. But at NYU, the group of, I will find the name, have done simulations that are really about large-scale structures, so how the primordial black holes modify the power spectrum. But they are at extremely early times. Then there is a recent simulation by Lewis Prohl, who has just put black holes, just think, if you know about simulations, well, you know about simulations because Yoki explained them to you. Sync particles, you just put black holes with the same properties as normal black holes, but just everywhere in the simulation. And then, well, I would have not done the simulations that way. Let's put it like this. And then you can see, you know, how their evolution affects the rest. I think that in this second type of simulations, the presence of the primordial black holes is completely decoupled from cosmology. I mean, it's just, you know, they're just distributed without considering that they would affect their environment. I mean, if I am a dark matter particle at redshift 2000 and have a black hole near me, probably I would kind of be dragged towards this, but this is not included in simulation. So I think that there is a lot of work that can be done, but it's extremely complex because of the time step required. So the simulation by Prohl got to redshift 20, so you cannot see anything about the interaction with stars, well, very little.
So a bunch of these pathways require, right, like early massive metal-free stars, right? But how well understood is the late stellar evolution of those stars? Because that can be tricky even for like massive stars in our galactic neighborhood to get right.
Now, honestly, the expert here is more Andrea than me. So if he feels like replying, I...
Well, I think that for some reason, actually, the primordial stars are a little easier to process than the evolution because there's the atmosphere is simple, there is no opacity, so many properties are easier than you want to display a solar type star. So I think that I could say that we understand very enough the final stages, particularly for what concerns the very final stages where you have extraordinary stability, because you don't have the problem of the remnant, so everything is blown off. And the fact they collapse into a black hole is just an energetic consideration, which I think is hard to avoid. So I think we're pretty safe on the stellar evolution part.
Thanks.
I'm a bit confused about the primordial black holes. Do you know like what the fraction of them would be? Like, do we expect to find a lot of them, or is this some exotic thing?
Well, I mean, the number density could be whatever. The important thing is that the number density is below what is permitted by these models. I mean, so there are many different ways of forming primordial black holes. So, point one. Could be phase transitions, could be tails of the density distribution. So you can mix and match as well. Okay, if you're a theoretical physicist with a favorite primordial black hole model, probably you can predict your own number density. But then what you have to check is that you are below these limits. So if your favorite model predicts a number density of black holes that is 10% of the dark matter, no way. In fact, the main point is that the total fraction of matter that is in black holes is between 10 to the minus 6 and 10 to the minus 10, depending on the mass that you're considering. And so, it's basically outside this plot. So this is what saves these models. But the specific prediction on number density depends on the specific model for primordial black hole that you choose. More questions? Yes?
I would like to question about intermediate mass seed that is runaway model. I was wondering in the late stage of this model, we require these black holes to merge with each other,
Yeah.
right? However, I think the time scale of merger via gravitational radiation is much more longer than two-body relaxation. So
Yep.
I was wondering if we could only observe this kind of model in relatively low redshift.
Yeah, that's exactly the point. I mean, the hierarchical black hole formation mergers. So if you rely on the mergers of black holes in star clusters, this is expected to happen. Well, low redshift is a big word. At lower redshift, so it takes about 1 billion years to happen or so. Also, the success rate is not super high because you have to fight against the gravitational recoil. But definitely, I mean, if you look at the most recent analysis, Arcased or Antirattala, what they see is that the most successful cases are those with significant stellar mergers. And then once you already have a black hole with a few hundreds of solar masses or 1,000, then you kind of trigger a higher hierarchical merger. Because if you have a high mass ratio between the largest black hole and all the other black holes, the gravitational recoil velocity is very low, so you don't eject them anymore. This is also work by Gultekin in 2004 and 5. Okay, we have 9 minutes. Do we want to start the next chapter or shift the coffee a little bit?
Is the coffee ready?
Coffee is ready as it's according to the timetable.
Okay, so perhaps.
So we can start.
Okay. Okay, now the growth of black holes. 9 minutes of growth. There are 3 main ways for black holes to grow. One is gas accretion. That's when we see black holes as AGN or quasars. Black hole mergers. That's when we see them in gravitational waves. And accretion of stars. And that's when we see them as tidal disruption events. I think there hasn't been much discussion of tidal disruption events at all at this meeting. So, I will say a few words. Just in terms of integrated constraints, Sultan's argument allows one to estimate how much, the amount of growth driven by gas, meaning in the phases of AGN and quasars, over the last, as long as you trust your AGN luminosity function. A very nice argument brought by you and Tremaine in 2002 is that if you take black hole mergers, the total mass density in the universe on black holes will never increase. Because if you have 10 black holes of 100 solar masses, at most you can have 10 by 100, 1,000 solar mass black hole. Actually, you lose some mass because emission of gravitational waves carries away some of the mass. Accretion instead adds mass into black holes over time. So what you should see is an increase in the mass density of black holes over time. We're talking about density simply because we count things within cubic megaparsecs. If we were to see the all observable universe, we could talk about the total mass in black holes in the universe. Now, if you integrate the AGN luminosity function, so using this Sultan's argument, you can show, and I will show the argument in a minute, that the mass density in black holes increased by about 2 orders of magnitude over the last 10 billion years. So accretion of gas is certainly playing an important, if not dominant, role in the growth of black holes in the observable universe. This has to be contrasted with the high redshift. What's going on there? Now, this is an integral. Okay, this function is an integral. You start from high redshift, you integrate over time, and you get a cumulative function. This is reported here. These points, instead, are obtained just integrating the mass density in black holes in a small redshift bin. Okay, these are not cumulative, also because if they were cumulative, they would. So if all the AGN that we're seeing with JWST are AGN, we have accumulated more mass density in black holes at redshift 8 than from redshift 3 to 2. Now, this is bizarre. So, this is one of the reasons why I'm still a bit wondering if everything that is called an AGN is really an AGN, because it really breaks all the nice laws that we have seen before. Now, already in this paper, there are ways to get away with this. Part is bolometric corrections. You can dust, spin evolution. You can get away, but this is a bit scary. So, what is Sultan's argument? It's very elegant. As I said, it's super elegant. So, luminosity is epsilon dot c squared. I think that no one needs an explanation there. Okay. So if a fraction of the accreted mass epsilon goes into luminosity, one epsilon goes into the black hole. So you can rephrase the luminosity as the accreted mass, but then if you integrate over time, instead of talking about luminosity and the accretion rate, you get energy and total accreted mass. This is for one black hole. Sultan's argument says, well, let's say the luminosity function of AGN, this is just the integral. So if you integrate the luminosity function of AGN, dn over dl dv, over luminosity and over time, just going from redshift to time, you get the total energy density ever produced by AGN. Now, since the energy scales with the accreted mass by epsilon 1 minus epsilon, then this integrated total energy can be translated into an integrated total mass density. So just from the luminosity function of AGN, one can obtain the total mass density ever accreted by black holes in AGN phases, minus this free parameter epsilon, which in first approximation is given only by black hole spin, but it's very complicated. So if you're interested in epsilon, you can ask me. I'm not going to discuss here. So based on this argument, as I showed, accretion leads. So, sorry, let me go back here. This argument is what tells you that black holes have accreted 2 orders of magnitude of mass in the last 10 billion years. This same thing here. So what about black hole mergers? Are they important like ever? So statistically, not much. But they can be important in specific mass ranges or galaxies. Basically, if you look at theoretical models, black hole mergers are important wherever there is no gas. In gas-poor galaxies at low redshift, black holes don't have any gas, so they grow by merger. So this is typically important in the most massive galaxies, so like BCGs in galaxy clusters. There you can show that based on theoretical models, black holes have grown 50% of their mass in the last couple of 5 billion years just by black hole mergers. If you instead go to black holes of like Sagittarius A star, Milky Way, the fraction of mass contributed by mergers is tiny. This doesn't mean that the black holes have not merged, especially at high redshift. It means that the contribution to the mass is small. Now, this last concept, and then we're going. The Eddington limit, these words have been used over and over, has been defined already, I think so. Anyway, just, if you think of stars, that's a beautiful case in which you can have the Eddington limit when you compare radiation pressure to gravity. And for stars, well, okay, it can work, not always. But in general, if you are in a spherical geometry and you only have hydrogen gas, the Eddington limit is correct. For black holes, usually you're not in spherical geometry, and usually you don't have only hydrogen. So the Eddington limit is not actual limit. What we talk about is the Eddington ratio, which is the ratio of the luminosity to the Eddington luminosity, but does not need to be a number less than 1. And I will stop here for now. Sounds good?
Thanks, Marta. We have coffee. We come back 10:30 sharp.